So, no more questions for the preceding speakers. So now, I have the pleasure to introduce Professor Dr. Stefan PICKL, who is one of my best scientific friends since a long time, and I'm really happy that he came in Liège, because he was in my congress in computing anticipatory system. Practically, I teach of the 10 congress 20 years, we know. And he told me, when you make something in Liège, they will come soon. And he came from Asia right now, today, and tomorrow he has a defense for a PhD thesis. So he just take a few hours to be with us at Vichy. So I thank you for that to you. And your paper is about integrated assessment models and their resilience on complex networks. Please, we hear from you.
Yes, Daniel, really thank you very much for this invitation. And as he mentioned, Liège is for me very specific and very unique, because, and this is a reality, the conferences of Daniel were distinguished. They were a high scientific level, but there was also a very, very great hospitality, an international hospitality, which I never had at any other conferences. And I was here 5 or 6 times when you did CASIS, and for that reason, when he asked me, Stefan, could you come? And I said, Daniel, normally I come for 3 or 4 days, but I can do it only on Wednesday. And he said, you can come, and then I come, but I told it to your colleagues. There was a fire between Cologne and Bonn yesterday, and the railway were closed. And it took me 10 hours today. I give you now a 30 minutes talk. I'm not a specialist like you with quantum theory and theoretical physics. I tell you a little bit what I did 20 years ago when people were laughing on myself, and then what I learned from Daniel with anticipatory systems, and maybe we come to the so-called climate problem. I'm dealing, or I'm working on, as you see also on the book, can we understand a little bit complex networks? And I would like to tell you a little bit about energy networks, about optimization on these networks, and how can we develop a little bit of risk methodology. And if you look behind, you will see that it is a little bit what you mentioned in the talk before, that if you do some analysis, you will see you have immediately a nonlinear behavior and chaotic behavior. The motivation, we are connected with IBM, with smart cities, and but in the year 2003, when I went to CASIS, there was the same summer, and it was very, very hot. And we developed with a small company in the US a software which helps to manage the world's environment. We simulate CO2 and said that we can do it, but nobody was interested. This was maybe the situation 92 with Rio de Janeiro, the Kyoto Protocol. And in the year 98, I submitted my PhD, and the dean came and said, Stefan, this is nice physics, but put away the environmental topic. Nobody is interested in it. CO2 emissions, but then I went to Daniel and he said, you have to forecast. You have to predict in an anticipatory way. And this was 2002, an advertisement, not of Daniel, but of BASF. The large chemical company said, we have to look into the future. We have to predict a little bit. And last week when I was in Singapore, they have an institute for strategic insight. And my feeling is that what you discuss here, to understand complex behavior, to predict, will become more and more important for the scientific world. We are doing some decision making. Maybe you know the so-called TÜV Süddeutschland. This is a company which advises the government in a non-profit way. And I'm working also together with Ernst Ulrich von Weizsäcker from the Club of Rome. And he's also interested in your models. He said we need new economic models. The old economic models are not reasonable enough. I would not like to bore you with a climate system, but what is interesting nowadays, yesterday in Singapore, the temperature is lower than here. And since 7 days in Singapore, normally you have between 5 and 6 a thunderstorm. I had there 7 days no rain. You see, the whole world, the climate system is in an imbalance. This was the situation of CO2, and we are now here. Yes. What can we do? Can we understand a little bit this complex behavior? And when the director of the Columbia University Earth Institute visited my institute, he said, the politicians play games. We have to analyze these games. And then I developed a model, and maybe we can discuss with you here a few aspects. Behind is a physical model, and I developed a very, very simple nonlinear time discrete model where I have for each actor, it's a game theoretic model, every actor has a level of emissions, and with financial means he can reduce, he can make the models more efficient, he can reduce or increase the financial budget, the emissions. We have a growth parameter, a memory parameter, and a so-called matrix of effectivity. This is a very simple model, and Daniel very often criticized it and said you have to introduce more complexity. But what is interesting behind? In the center is a matrix of effectivity. And this is mentioned explicitly in the Kyoto Protocol. And I would like to present to you until 6 o'clock only two aspects which are interesting. We can on one side define a game for this matrix of effectivity, and on the other side I develop an algorithm which is not finished yet, and maybe you have some ideas for it. If we do some simulation on the left side for the emissions, on the right side for the coast, we did it together with Santa Fe and also with a university in Malaysia. And I would like to show you what can we do now with that model? How can we understand it in an efficient way? And for some parameters, you observe a nonlinear, a little bit chaotic behavior, which is very, very similar to real-world data. And then I say,
what is that data of?
It's the emissions for financial investments, yes. And now we say the following. If we take this as a mathematical model and we normalize it, as a mathematician, I'm not a physicist, let us try to control the model in such a way that we reach a desired level in a normalized scenario, and after 10 or 15 years, we can reduce the financial investments. That means we put at each time step t a control parameter and try to calculate it in a first step. If you are a specialist for such control system, you see immediately these are fixed points, and then you have a fixed point control with state and control parameters, but you cannot solve it directly. And the first attempt is you took a so-called approximation model. If I cannot control it directly, I can say I introduce a so-called approximation function and try to solve it. And if I can solve the approximation problem and the solution converges to my main problem, then also my control parameter converges. this is a little bit nice control theory, and for example, this is the original problem, and you make a transformation, and then you have to guarantee that at each time step, and here it comes again to your physical interest, that you go exactly through the fixed point in that trajectory. And I wrote a book on time discrete systems and dynamical games, and I would like to show you now why is the algorithmic framework connected with dynamical games. We control the process, we have the matrices, and now the idea is there a game? How is the game connected with emission trading, what is discussed in the news? If you look again on that equation, and you say if we have a cooperation between Germany and Belgium, and if I say we would like to cooperate, that means if we invest in a power plant, then the so-called matrix of effectivity has to increase. And if it increases, you see immediately the financial investment, the costs go down. This means it's a co-financing, but maybe I was so angry on that person who did not stop the train. I did not miss Belgium, but maybe miss France. That means I cooperate with another partner. And now you see what happened in that game. I have a certain amount and I look in the dynamic behavior, which partner am I able to control? And this is also mentioned in the Kyoto Protocol. And then I invented a so-called game without cooperation and with cooperation. And I looked again on the physical system and I said, how is it possible to control the game, to analyze the game? For which values can we guarantee in the next 10 years the reduced scenario? And I calculated a so-called upper vector for every player in the room. He said, I would like to reach my desired fixed point. On the other side, we have a certain gap. We have only a certain budget, and we have concession. That means a bargaining. And I will not go too much into details, but you see it's a little bit connected. It's not so easy as it seems. But I have, for my friend Daniel, a certain present. Because if Daniel is now asking, you are sitting here in the room, with which person should I cooperate? And then he will say, okay, I will cooperate with you too. And then he offers to you the maximal amount of bargaining value that you stay with him in that power plant cooperation. But then your gap is too high for him. And he's asking the other persons. And now you see why there is a game theoretic behavior in the control process. And he will ask, I would like to reach my fixed point with you, but besides of that, I would like to minimize my financial amount. And this is a little bit a two-stage game. On one side, he would like to minimize the gap, what he's giving to you, and on the other side, he would like to maximize his fixed point. And the question behind is now, and this is a little bit, I would say, a topic for Virgil maybe in 2 years when I come again. This was done for Daniel. But you are saying, oh, if Daniel is so smart, I do the same. And then now you are in the middle and ask again all of these groups and coalitions. And then you see how a large complexity increases. And this means a high combinatorial structure. And I call this game a Kyoto game, and we are still in understanding the complexity behind. You get a so-called non-differentiable system of highly nonlinear equations, but you can solve it. You can solve it for several points, and we are analyzing the structure again of the matrix, and we do some non-smooth analysis, and then you see the chaotic behavior can be controlled in such a way. This is a little bit the motivation for the game behind. What is the idea? You have at certain time steps t, and together with my colleague Dimitri Lozovanu, who published also in the proceedings of Cassis, you calculate now what is the optimal coalition at each time step in order to reach this desired game. And we published some results also at Cassis about Nash and Pareto equilibria in that book. This is a little bit the generalized decision process, and the idea behind is you connect signal theory and graph theory. Yeah? If you're doing this, you will say you calculate matrices, but do you know, are these matrices are exact? Where do you get the data? On one side you're doing high theoretical analysis, on the other side you're dealing with CO2 data, which is not so certain. There's a lot of uncertainty, and this is a little bit the second part, and maybe this is more closer to you, and maybe you will criticize about my approach. How can we identify CO2 matrices for our game which are handled and not handled? And for that reason, I apply Euler's method, and I ask for which matrices of effectivity is a process stable or not. And there is, and this is a little bit also what is your vision. You cited also the Feynman lecture, and here I cited Crichton and Tom. And they said if you have a certain set of matrices, the set is stable if and only if the following set is bounded. What is B? B is a so-called convex hull of a starting set, of a starting game theoretic set, multiplied with the matrices. That's all. The mathematicians are happy, but you will discuss now. Because we don't like this theoretical result, because we cannot embed it in our game. And for that reason, the most important thing here is one word. The word If there is a B0, and if that means there is not the B0, we can say we take any B0 which is very convenient for us. And that means we take a very simple one and we took only the extremal points of that B0. And the power of the algorithm is now, do not go until infinity, try to avoid to go until infinity. And I would like to explain only to you the idea of that algorithm, namely, if Z is an extremal point of pk, it can be calculated by the previous extremal points. That means you have only to consider the extremal points of that polytope. In reality, we have polytopes with 100,000 points, and not 2-dimensional, but 10 or 12-dimensional. And then we calculate, multiply again with m power to 2, with m power to 3, and if this polytope increases, we build the convex hull. Should we go until infinity? No. We would like to avoid this. That means when is the convex hull totally constructed? If we multiply again and then we go inside, then we are done. What does this mean? We calculate and we are going inside, then we have constructed the next polytope. You might say, this is very easy. Yes, if we have only one extremal point. But we have several players. That means what happened if this extremal point begins also with a multiplication. And this is again a little bit in the heart of your conference and your discussions and what I discussed also with Daniel. How can we understand if we have two equilibria? How is the so-called exchange of information and energy? And I call it here the so-called oscillation of extremal point. And then you get a decision criterion. That means if we have the B0 and the BK and the intersection set of the extremal points is empty, then we have a stable behavior and we calculate it in Dutch way. Maybe again 5 minutes. Is this now everything? I would say it's a nice application between physics and mathematics. And you see between dynamical systems and discrete mathematics, there is a connection. I made a mistake in my talk. I showed to you and I said to you, it's enough to check only the extremal points. We learned if we start with one B0 and we have a BK where the intersection set is empty, then we are unstable. If we check only the extremal points of the blue and the red, the green, the intersection set is empty. Also there is an 4-star intersection. And for that reason, we have to be very careful with such a situation. Even if you have 100,000 points, it's very difficult. What are we doing now? We are trying to analyze, to search certain research directions. In which direction is a process more stable or not? And this is also still an open problem, and maybe I can learn from your ideas. We put this in a small software and we presented it also in Brussels, but it's a very simple software, and you see here you have some agents, some accounts, and then you make a little bit of an analysis. My feeling is that there is a common field between environmental and physical systems and nonlinear behavior. This is a document of the United Nations, and you see that we have a very hot summer, and the problem is how can we handle with it? And we need to understand uncertainty, and this is maybe what I learned also when I studied your papers. How are we able to understand a complex system? Yes, complexity. And at the moment, my attitude is that the CO2 allocation is not fair, and I'm interested in the philosophical discussion. What is fair and how can we change the fairness of the actors? How can we take it to a serious action? And at the moment, maybe the world is like a climate change supermarket, but I'm optimistic that if we have such conferences which Daniel invented and Amoroso, we can go a little bit further to solve these problems.
Just keep the slide. You got your photo? Thank you.
I would like to conclude, and I showed this maybe also at Cassis.
Can I help there? Yes. Yes, it's marvelous.
I don't like that your physique is so handsome.
I know what to do with Amoroso. In fact, it's Richard. And it is Dubois.
I made this when I wrote my master's thesis in Switzerland. And And the ideas I learned from Daniel. Daniel would say a physicist can prove that the paraglider can fly. And a material scientist can minimize the weight and maximize the flight time. An economist might say, oh, this is taken in Switzerland, this is crazy, it's too expensive, go to Austria or Sweden. But at the end, and we discussed this, it's the human being. You have to understand the human being. Are you willing to go into the fog, into the uncertainty? It's not only one discipline, it's a multidisciplinary approach. And for that reason, it is not enough to wish, you should apply it, and it is not enough to transfer, you should do it from Goethe. Daniel, thank you so much, and I hope I can come in 2 years,
Definitely.
for 3 days.
You can have it in
But
Paris, so you don't
who
have
has
to...
never been at Cassis, give us a chance maybe to do once again one. These were wonderful conferences. Thank you to the...
Thank you.
Thank you.
Question?
I'd like to propose a solution with the slide on the table to the problem. I think the solution to the problem is to look up on this slide and see the sunshine. Look for the opportunity. This is beautiful. Beautiful. But just wait a second. What needs... Fantastic. You knew. That's lovely. And see the opportunity, but the way to solve a problem is to recognize the problem and then to fix it, and to put the money where that fixing is, and to put the resources where that fixing is, directly, single-mindedly, with the proper kind of resources that one needs, the kind of resources that one might put into CERN. Maybe you want to put them somewhere else.
Yes.
The sort of things you might want to take to build some missiles and fire them in the USA from North Korea, likewise. The problems are coming from the fact that where we're putting our effort is in the wrong direction.
Yeah.
And we know how to fix it. There's a huge energy source up there. We just use it to sequester carbon dioxide directly. End of problem. Just do it. We can do it. We can do it in 5 years.
That's what they're doing in South Australia.
Absolutely. It's good, isn't it? I know there's some people working on that.
Maybe that hasn't happened yet, and maybe your analysis would show that it hasn't happened yet, because it doesn't include something that's a block in there, a control block or a feedback block of some kind.
Very good.
It includes corruption.
Yeah.
The problem is not, the problem with sun is, I know when I was a student 50 years ago, we already knew that answer.
I will add this. Yes,
And
it's
why it hasn't happened.
I will add this. It's very good. To make this is a little bit what I meant with stable, but you are right. Yes. Yeah.
What do you think about perspective of using mathematical apparatus of quantum mechanics or including quantum games in your topic? Is it useful or not? Yes
I
or
would
no?
say it's useful, but I'm afraid that I'm not so good as you in quantum mathematics to understand it. But I would say that in the next 50 years, this will be the next decade of understanding. But you cannot do it in 2 weeks.
5 years.
Yes. No, you cannot understand quantum mechanics in 2 weeks or in 2 months. You have to deal 2 years, and then you can transfer it. But it's a very good idea. When I was in Cologne, when I was here in Liège, and my supervisor, he was a crazy person. For example, we run with his friend a conference in Italy. Once here in Italy, once here. I never brought him here to Daniel. I tell you the reason. And we had 10 papers from Germany and 10 papers from Italy. And it was a very familiar virtual on graph theory. And then the director submitted a paper, and I gave him this paper to make a small referee report. And in 4 weeks there was a conference in Italy. And he wrote 8 pages and rejected the paper. But no, he can destroy a conference. But I learned from him the following. He said, Stefan, We are working with negative numbers, but the Egyptians did not know this. Why are we not working with negative probabilities? And why are we not working with quantum games? And for that reason, I'm really convinced that this is a very good approach.
Yeah, many astronomers tell that the greenhouse effect of CO2 is almost saturated. What do you think of that?
Yeah.
Oh, one question. At one point you put John Nash's name up. I think you said Nash's theorem or something like that. Could you just show the slide again?
We work with Reinhard Selten, who was with him the Nobel Prize. We presented at the Cassis conference algorithms for the prediction of Nash equilibria in that system.
Nash equilibrium.
Nash equilibrium.
What are Nash equilibria?
Do you know Pareto and Nash?
Sorry?
Pareto and Nash.
Yes.
Optimistic and pessimistic.
Very good. Pareto said the following. There is an equilibria if the following occurs. If you said, if I will change, or Nash will say, if you change your amount or your steering control, you will not get better. And everybody is doing this in the room. This is a Nash equilibrium. Everybody has a control, a cockpit, and we steer, and if everybody is then, if this is a connected systems, steers again and you become worse, you say, no, I do not do it. Pareto, neglected in science, is much smarter. He says we need an equilibria in such a way, everybody is steering, and if I steer and she becomes worse, I do not do this. Pareto means the welfare economy. Nash means a non-cooperative game. Nash says only, I steer, and if I recognize, oh, I become worse, I stop. Doesn't matter with Daniel or doesn't matter with you. Pareto is much more difficult. But nobody is writing in the economy about Pareto because it's a cooperative behavior. But we try to make a cooperative approach.
OECD,
Yeah.
if I might say so. My father helped negotiate the founding of OECD.
Yeah.
And that was what won the Cold War.
Yes.
And my understanding is that that was all about cooperation.
Yeah.
And that came out of Nash's.
Yes.
I regard Nash as the originator of the system that won the Cold War.
I tell you the following, my 16-year-old daughter was with me in Asia 1 week for the first time. And she said, Papa, in Asia I feel that the people help each other. They are cooperative. If you are here at an airport or on a street, everybody is trying to maneuver its best behavior. We do not recognize this. But this is a little bit connected. And we would like to understand connected physical system, the cooperation behind.
I think you need a mechanism to force the cooperation. And I think that mechanism is a very simple one. I think that people don't understand where the origin of wealth comes from. And in fact, we're in control of it. Not we in this room, we collectively as scientists are in control of it, really. We have to take control and then force the thing to be for the good of people.
The force should be one of altruism.
Yes, absolutely.
It should be something which is structured so that it cannot benefit oneself.
And in the future, you will make your simulation on a quantum computer.
With your help. We at our university, we have a quantum computer since 2 weeks. And we would like to try. But I'm not sure if I will be successful.
So
I apologize again. I wrote at 4:30 to you.
I didn't get it.
No, I will come in 25 minutes. Relax. You will see this evening. Daniel, thank you again for that session. Thank you.